Alright, so chapter 5. Let me ask you, do you consider yourself reasonable people?
Yeah.
Would you consider yourself reasonable? Okay, so what do you mean by that? You're a reasonable person, what do you mean by that? What does that mean? Anyone can chime in. What do you think it means to be reasonable?
That you're not dumb in certain situations.
Okay, which is true. It's I understand what you're saying by that. In certain, and it's the nice catch-all in certain situations, but I am in others. So, yeah. So if you think about reasonable, we think about the word. You have to reason, and you're able to reason, and you are reasonable people because no matter, especially you would be more reasonable in certain circumstances. And I wouldn't call it dumb necessarily, but it might be ignorant. Just because you lack the knowledge necessary to understand something. But we all have the ability to reason through situations. Okay, I'm given this information, so how can I come to this conclusion? And it usually falls in with, I have an opinion on something, or I know this to be a fact because I've been given all of this information. I can answer this question because I've been given this information. But you're always having to kind of still put pieces together to get to those conclusions. Unless you're being taught specifically this, then this, then this, and so here's your answer. Does that make sense? But life isn't that way always. Your job, usually they'll teach you how to function, but there still requires some sort of problem solving to take place. Well, that's what we're going over with this chapter. Okay, it's going to require that you be reasonable people. Okay, you're going to have to take bits of information and with what you know, be able to reason through it to come to conclusions. Now, in order to organize yourself in doing that, there are words and symbols that we can follow to kind of put it up there so we can follow along clearly. Because if all we do is talk about this long drawn out topic, you're going to have to take notes to really keep up. And you'll keep most of it in your head, but you're going to forget something. And of course in math, we always like to have symbols that are kind of like shorthand. All the symbols we've been doing so far are basically a shorter way of doing something instead of actually having to write it all out in paragraph form, right? Instead of writing the word plus, we write this symbol. And you know, how many times would you want to write the word multiply whenever you could just do a dot, an X, or a set of parentheses? Right? It's a whole lot easier. Well, that's what we're talking about. But, as always, whenever you learn something new, it might be a little bit confusing. So as we go through and start talking about these things, make sure you write that this means plus. This means multiply. Okay, and same thing with definitions. Make sure on your notes that you are writing these things down because you're going to see them, we're going to use them, so go back to and refer to them. It'll help you out. Okay? I can tell you are already excited. This is going to be kind of fun. So, do you like challenges? Challenges are fun. You're like, okay, somebody said I can't do this, or this seems a little bit difficult. How good am I at figuring this out? And I love those. Those are, I love figuring it out. And that's really what we're going to be doing a lot of in this chapter, is you're going to be challenged, are you able to figure out through this information and come to the correct conclusions? Okay? Alright, so starting off with 5.1, the first part of that chapter talks about reasoning and understanding. It's titled The Introduction to Reasoning. The definition of reasoning is the step-by-step process that begins with a known fact or assumption, okay, and builds to a conclusion in an orderly, concise way. This is also called logical thinking, okay? It's not just random acts of emotion that are thrown out there where you're mad so this person did something wrong. Well, you're only saying that because you're mad at them right now. What facts do you have or assumptions that you can put in logical order that lead you to that conclusion? Okay? So we're going to be emotionless in this. You're not going to get mad and slam your pencil down and say, I'm sick of geometry. Right? Right. All right, cool. So let's look at, in 5.1, we're going to look at this one example of what's going on. Okay, and we're going to work through this together. Go team. Have any of y'all ever done a logic problem? Okay, so y'all done those as little exercises and stuff. That's what this is. This is essentially a logic problem. If you haven't done them, then you will see something similar, very similar to what we're about to do. All right, and with a logic problem, there is always some sort of box or table that's used to organize what you know and what you don't know. Because then you can eliminate possibilities based on information, and you can confirm possibilities based on information. All right, so let's read through this. Bob, Jim, Phil, and Brent are part of the crew of a commercial tugboat. Their jobs, not in any particular order, are captain, first mate, cook, and mechanic. The mechanic is the first mate's younger brother. The captain has no relatives on the crew, but Brent does. The first mate is not the cook's uncle, and the cook is not the mechanic's uncle, but Bob is Phil's uncle. So what job does each man have, and how are the men related to each other? Okay, so first we need to figure out who we have. We have Bob, we have Jim, we have Phil, and we have Brent. All right, and somewhere there's going to be a captain, there's going to be a first mate, there is going to be a cook, and a mechanic. So now we can, with this, we can end up drawing our table. And if it helps, you can also do this. I don't know if it will help you or make it more difficult. Okay, so let's go through with what we have. All right, because we've been given pieces of information without just being given the answer. All right, so we have the mechanic is the first mate's younger brother. The mechanic is the first mate's younger brother. So this is the older brother, this is the younger brother. So brother of first mate. And this is the brother of the mechanic. Why is this important right now? Labeling who is related to who. Why is this important?
It'll eliminate later.
Yes, absolutely. There will be an elimination. Because read the next sentence. The captain has no relatives on the crew. The captain has no relatives on the crew. So once you identify possibly people being related to each other, then we know if we've identified that somebody's related to another person, they cannot be the captain. Now they may be the first mate and possibly the cook, because we're not saying that the cook right now isn't related to anybody. So far, there could be an uncle, a nephew, who knows what, in which I think we find out some of that information later on. Okay? But the captain has no relatives on the crew, but Brent does. So what does that tell us? The captain has no relatives on the crew, but Brent does have a relative on the crew.
So Brent isn't the captain.
Exactly. Brent cannot be the captain, so we can put an X right there. Does that make sense? Okay. So, the first mate is not the cook's uncle. The first mate is not the cook's uncle, and the cook is not the mechanic's uncle. But Bob is Phil's uncle.
That means the first mate could be the mechanic's uncle.
Okay? Yes, so let's read through it again. The first mate is not the cook's uncle. The first mate is not his uncle. And the cook is not the mechanic's uncle. So we're going down the line. He's not his uncle, he's not his uncle. But it doesn't mean that we can't go this direction, right? The cook could be the mechanic's uncle, or the first mate could be the cook's uncle. Does that make sense?
No,
So-
the first mate couldn't be the cook's uncle,
Why is that?
because it tells us so.
Okay, good. See, so we're paying attention. So, and the cook is not the mechanic's uncle, he's not his uncle, he's not his uncle. So then, so let's continue on, but Bob is Phil's uncle. So, can we figure out who the uncle is in all of this? He is not his uncle. He is not his uncle. These two are brothers, so can they still be uncles? No.
So that means the mechanic is the cook.
That's right, the mechanic, and let's think about this. We'll do 1, M, and C. Okay, so there's going to be a combination. We know somebody is the uncle of somebody here because we were told that Bob is Phil's uncle. So if we do I and C, first and C, well, we already know that they don't equal the uncle. C and M, the cook and the mechanic, they do not equal the uncle. So what other combination is there? There is the C and the first mate, the mechanic and the first mate, but they can't be the uncles because they're brothers. So the only thing left, we have first and C, C and M, the cook and mechanic, and then the mechanic and the first mate, and likewise the first mate versus the mechanic can't be the uncle because, again, they're brothers. So the only other possibility is that the cook would be the mechanic's uncle. Okay, does that make sense? Or is that kind of confusing?
But it says the
Yeah.
cook is not the mechanic's uncle.
Okay,
I
good.
s-
Oh, yes, you're right. I did that wrong. The mechanic, because we already established that up here, I wrote it down wrong. I apologize. The mechanic
It's the cook's
is the cook's uncle. And I think it'd probably be easier if we drew an arrow who we're talking about in what direction. So the first mate to the cook is not their uncle, we've been told that. The cook to the mechanic is not the uncle, we've been told that. The mechanic to the first mate are brothers. The first mate to the mechanic are brothers. The only other combination left is the mechanic to the cook.
But the cook could be the first mate's brother. Though.
What's that?
The cook can be the first mate's brother.
The first mate's uncle?
I mean uncle, yeah.
Is that possible?
Yeah.
Yes, the cook could be.
Yeah, because it just says that he's
Okay.
not the
So the
mechanic's
cook,
uncle.
good. Yes, we are only told that the first mate is not the cook's uncle, okay?
That way, if the mechanic is the cook's uncle.
Okay, so this is what we have so far. Now we've established we're going to be looking for this somewhere because we've eliminated these, all right? And I'm glad that you saw, and this is part of this reasoning process. At first glance, you can think, okay, yes, this is what we're left with, but there may be pieces that we're not considering. So sometimes, what I'm trying to demonstrate here, sometimes you need to stop what you're doing, go off to the side or get some scratch paper, and kind of work through some of your options, especially with combinations. And even eliminating combinations helps you get closer to your final answer. It may not get you to your final answer yet, because right now we have two possibilities, right? So now what this says, it tells us after that, but Bob is Phil's uncle. Bob is Phil's uncle. So what two and only two possible jobs on the crew can Bob have?
The cook and the mechanic.
The cook and the mechanic. Because one of these two is going to be the uncle, right? And Bob is Phil's uncle. All right? So Bob, we know, is not the captain and not the first mate. He has to be one of these two.
Phil isn't either one of those
Okay, and why is that?
either. Because he's related to Bob.
Okay, he's related to Bob, he's his nephew. Okay, he's his nephew. So, which means Phil cannot be what?
The captain.
Cannot be the captain, because he is Bob's nephew. So now we know that Jim is actually going to be the captain. So we'll put that off to the side. Jim equals the captain. So then what we can do is X these out, especially visually. We already know he's the captain here, but visually sometimes it helps us to go ahead and start eliminating things. Okay? Now, this is all the information that we have, so how do we reason through? We know that Bob is Phil's uncle. So then they cannot be brothers, right? So since Bob is the mechanic, could be the cook or the mechanic,
Oh, that makes Brent the first mate.
how does it make Brent the first mate?
Wait, we said Phil and Bob. Wait, no, Bob is the cook or the mechanic. And Phil is his nephew.
So let me ask you this. If Bob is Phil's uncle, what does that leave Brent?
Phil,
Oh.
your uncle?
What?
No, we're the only one.
Brent is going to be the brother of one of those two.
It said
Because we have two brothers as far as a
the
relationship.
mechanic is the first mate's younger brother. So if Bob, so that makes Brent the brother.
Of who though?
Bob.
So
Are you sure?
he would
Well,
be-
because you said Bob was the uncle,
Mm-hmm.
and since he's either,
Bob is Phil's uncle.
I know, it said the mechanic is the first mate's brother, so if Bob is the mechanic, then Brent would be the,
If he's the mechanic, then yes, then Brent would be the first mate. But if Bob is actually the cook,
but it
then not
makes,
necessarily
but
so.
it makes no sense that the nephew would be the, hold on,
No, okay. Wait, Bob is the mechanic, and then Phil is the cook because Phil is the nephew. Wait, no, never mind.
Keep going.
Like,
I had something where if it was brothers, then the cook couldn't be the uncle because he's the nephew or something. I don't know. Let me see. The first the mechanic is the first mate's younger brother. but Bob is Phil's uncle.
So let's think about this.
Okay, yeah, no, it makes sense because if Bob was the mechanic, then Brent would be the younger brother because Phil is the nephew, meaning he can't be the first mate because the first mate is Bob's brother.
Did y'all follow that? So who are you saying is the first mate?
Brent.
Okay, so let's say, tentatively, we'll do a squiggly line. Let's say he is the first mate. Okay, then this should work, process through, and be accurate. If he is the first mate, all right, then that means he is the, and then we'll do a small x here. That means Phil can't be the first mate. Okay, which means he is going to be, Brent is going to be the brother of who?
Bob.
Wait,
Okay,
yeah,
now, we know Bob is the uncle, okay? Which means that he is going to have to be the uncle of Phil, right?
Mhm.
So then where does that put Bob? What would he end up being, the cook or the mechanic? Go ahead.
he'd be the mechanic because since Phil is the uncle, he can't be the brothers, so you'd X out on the brother. No, Phil.
You said Bob is the mechanic, right?
Oh, yeah.
Mhm.
And then, yeah, so Phil couldn't be any brothers, so he would be the cook. And,
Now, why is Bob the mechanic?
because that's the only other thing.
So if he, and let's reason through this. If he was the mechanic, he's not the brother of Phil, he has to be the uncle of Phil. Okay? So then that would mean that that Brent is the brother of Bob. What if Brent were the brother of Bob? I'm sorry, the brother of Phil. Let's say, what if Phil were the mechanic? Those two were brothers. Then we put Bob here, he would end up being the cook. Which means he is also the uncle of Brent. Is that accurate?
No.
No, he's not the brother or the uncle of Brent. So then we know that that's not accurate. So what y'all determined was actually correct. So Bob is what again?
Mechanic.
Mechanic?
Phil is the cook.
There we go. Y'all have figured it out. Now again, sometimes it takes some of that reasoning where you may even have to follow the rabbit trail down a certain way and make sure everything lines up and it'll be accurate or it won't. And so we went both ways and we found that one of the ways couldn't be a possibility. You can start off as possibilities, but in the long run, it won't work out. Okay, so then you have to backtrack and then try another rabbit trail. And then, because sometimes you're given most everything you need to figure it out, it's just a matter of yes. But others, you actually have to take some of that information and apply it to see if it makes sense or not. Okay? Sound good?
Yeah.
Good job with that. Really good job with that. And the fact that you are paying attention to detail, that combinations is a huge thing. So then we found that Jim is a captain, Bob is a mechanic, Phil is the cook, and Brent is the first mate. Yes. All right, any questions about this? All right, good. Now, we spent about 1/3 of our class time on just this one problem, but it is very important that we establish this type of understanding, because now that y'all have gotten a good grasp on this, it's going to help with these future sections, okay? And here, the next several sections, you are going to have to make sure to take good notes with this. Okay, so 5.2, statements and quantifiers. Statements and quantifiers. So we're going to start off with these 5 statements on the top, or underneath 5.2 on page 166. George Washington was the first president of the United States. Number 2, 2 times 3 equals 9. Number 3, x plus 5 equals 23. Number 4, the Bible is the Word of God. Number 5, 8 plus 7 equals 15. Okay, taking into those phrases, okay, let's look at a definition of a statement. A statement. A statement is a sentence that is either true or false, but not both. It is either true or false, but not both. So is number 1 a statement?
Yes.
Yes, he was the first president of the United States. Number 2, 2 times 3 is 9 equals 9. Is that a statement?
Yeah.
Why?
Because it's false, but it's still a statement.
That's right. It's false, but it is still a statement. Okay? What about 3?
No, because x plus 5 isn't. Well, I mean, it's still a statement.
Is it
'Cause-
true
No,
or is it false?
it's false.
Oh wait.
How do you know?
Oh wait, no, it's not a statement.
Okay, why is that?
Because you don't know if it's true or false.
Exactly. We don't know what the value of x is, so we can't determine if it's actually true or false. So it's not considered a statement per se. Now, what you will hear is, and now this is geometry establishing statements in this perspective. However, and I do want to kind of clarify, in other areas of math, this would be considered a mathematical statement, so to speak. Okay, it's just a phrase of x plus 5 equals 23. And then we can determine what x equals, but just what was stated right here, we don't necessarily know what x equals. Okay, does that make sense? Okay, just because you will hear that term in the future mathematical statement. The Bible is the Word of God. Is that a statement? Yes. And 8 plus 7 equals 15. That is also a statement. Okay? So now we understand that it can be a true or false statement, but it cannot be both. All right, now, as we go on, statements are usually identified or symbolized with a lowercase p or a lowercase q, and even so much as a lowercase r. Now what's happening whenever you see this, we're starting off with lowercase p, and this will be the first statement that we come across. Okay, this p equals first statement. Q would be the second statement that we come across. And then R would be third. And then what do you think the next letter that we would use? What would it be?
S.
S, lowercase s, and so on. Okay, as we start adding in more statements. So whenever we see lowercase p or q, then we're saying p was that first statement that we made, q was the second statement that was made, and now we're going to be talking about relationships between them. So instead of having to write out this whole statement over and over and over again as we keep talking about it, we can just use simple letters of p, lowercase p, and lowercase q. Does everybody have that? Okay. Now, so we can have statements that are true, and then they can also be negated. And as we look on page 167, at the top it says, gold is a precious metal. Okay, that is a statement. Okay, and so let's say that we're going to use lowercase p as gold is a precious statement. Okay, now this is a true statement, but we can take the negation of it, which means gold is not a precious metal. And if we were to take the original statement, gold is a precious metal, and negate it and say, we'll change it to gold is not a precious metal, then we would symbolize that with a squiggly mark and a lowercase p. So this means not, and then whatever that statement is. That little squiggly line stands for the word not, or not statement, not P, not Q, not R, not S. Okay, now understand that it is the negation, does not mean that it's false. Okay, so if this was a true statement, then this would negate it. This is, so this would say this is not. If P started off as a false statement, let's say gold is not a precious metal, well then the negation of that would be, or the not statement would be gold is a precious metal. So understand it's not necessarily making it false, it's just taking the negation of that other statement. Does everybody understand the difference? I said it multiple times in brainwashing you. Okay, cool. Now, another symbol that we will use is the term all and every. And so as we look in our book, all men are sinners. Okay, so we can look at the statement, men are sinners, but then we can use this symbol, and it's an upside down A. Okay, and that stands for all or every. So then all, if the statement was men are sinners, and then we wanted to include all men, then we would actually write that down as this right there. The upside down A with P, the lowercase p. So all or every, and then whatever that statement is. Again, shorthand of being able to do that. And then, so all is considered a universal quantifier, okay? So it means it's a blanket statement. Now, there's another type of quantifier, which means that there exists one or more of. And that's going to be the backward uppercase E. And that equals one or more. Now, notice the difference between this and then the all every. All every means it applies to all of our components or every component. With this one, it means that there's at least one, or you would hear the term there exists at least a certain amount. Okay, so there has to be at least one, but there can be more than one. Okay, but not necessarily all of them. Okay? So a couple of examples of the negations are in that table at the bottom of page 167. Here it says, all flowers are pretty. So the negation would be, some flowers are not pretty. So notice how it negated this statement, because that first statement actually has two pieces to it. You have your all every, and then you have your statement. So then we need to negate both components of it. So if it's saying all, then now we have to say some. And then go to the statement, flowers are pretty, flowers are not pretty. Okay, so you'll understand how you're negating both components of those statements. Second, there exists a student who gets straight A's. So the negation would be no students, or there are no students who get straight A's. Okay, so we had this, there exists, and then whatever the statement is, we negated the there exists, and then we negated the statement itself. You got it? That's pretty easy, right? Go
I have a
ahead.
question.
Mhm.
When we need to put the little negative or whatever,
The negation squiggly? Mhm.
Do we put it in front of, like, do we put it in between the E and the P, backwards E and the P, or do we put it in front of all of it?
Now, well, technically, honestly, you can notate this however you want to. You could do this, okay, to where it applies to everything. You technically could do the negation of this and the negation of this, or you can throw in symbols or whatever. Just as long as somehow you show that that negation applies to both of these.
Okay.
This, I think, is easier. To me, it's less writing, and it makes sense. So, all right, good question. All right, so that is all with, now, if we were talking about negating both statements, like you had, let me ask you this real quick. You were told to negate these two statements. Oops, wrote that wrong. Okay, so how many statements do we have up here?
4.
Two.
Well,
2 statements, actually. Yes, it's just these are attached. The all every is attached to the first statement. There exists, or there is one or more of, is attached to the second statement. Okay, so you actually have 2 different statements up there. Make sense? Cool. Any questions about this? All right. That's 5.2. Now, you will be asked to identify whether statements are true or not true, or if they are a statement at all on your homework. And then you will be asked to write this. You'll be given statements. If y'all look on page 168 in your homework, looking at 13, you are given a series of statements up above. And this is the B exercises. So from those statements, you are given symbols. So then you are, say that number 13, you're given this. So then you will actually write out the all every aspect of statement R. Okay, so that would be statement R, men are bald. So your answer would be all men are bald. Easy enough, right? All you're doing is writing out what the symbolizes, what the symbols mean, and rephrasing the statement. I think that's going to be pretty easy for y'all. All right, 5.3. We are going to be talking about truth values and connectives. Primarily the and the or. And this is something that y'all will have to kind of memorize. You'll want to write down notes for, but you'll actually get it once you use it several times. Okay? Many times we're going to have to determine the truth value of a statement. Okay, we're going to have to reason to a conclusion, and you have to be able to build your arguments and your true statements in order to be able to substantiate that argument. Okay, and that's what we're kind of going to be looking at, especially with tables. All right, so for instance, we have what's called truth tables, and on page 170, now, what I want to make sure we understand on this is we have statement P, and then we have the negation of P. Okay, so if your original statement is true, then the negation of that will be false. Okay? If the original statement is false, then the negation of it will be true. Makes sense, right? If only it stayed that easy. There are some of these tables that would fill up this whole board, but we're not going to get that big. So it helps us to be able to relate and kind of build from there. If one statement is true and then we start talking about the negation, well then we know that it's false and we can build from there. And so that's what we are establishing. So simple statements can be combined with connectives, and we're going to be using the words conjunction and disjunction. And some of y'all may have heard this before in some of your other maths. The biggest component to consider with a conjunction, it's the word and. Okay, disjunction is or. Conjunction is and, disjunction is or. Now the best way to remember this is through symbols. Okay, so this symbol stands for conjunction. Now the best way to remember this is this looks like the capital letter A without the bar going across. So just consider the TP or the almost the A, that is and, which is conjunction. We have or, which is the V or upside down A, and that is a disjunction. Okay, so if we're talking about statements and we say that it's P in conjunction with Q, which means it has to apply to both. It is P and Q. Okay, otherwise we would have P or Q. It would be a disjunction. Now in reasoning or establishing parameters, it's important to be able to have either one of these. Okay, so in order to open this door, I have to move my feet and walk across the floor. Okay, it takes both of those to do that. If we did or, I would have to move my feet or move across the floor. Well, it doesn't quite work. I can't move across the floor if I don't move my feet. Does that make sense? So in order to accomplish that goal, it has to be both of those. And like we talked about before in our other class, I can take this pen and I can either lay it on the table or on the floor, it doesn't matter. Okay, well I can accomplish one of those and so still make this work out. But to do on top of the table and on top of the floor, well, that's not going to work. Okay, I can't actually do that. This marker's not long enough. Make sense? Okay, so let's look at a table. Does everybody have this written down? Okay, good. We'll look at the table that they have in the book here, and let's do this together. Page 170 at the bottom. Okay, and it's important that we look at this. If we have, and P and Q again are two different statements. So if P is true and Q is true, then the disjunction of them would be true. Okay, because you only have to accommodate one of those statements in a disjunction, right? It can be either or. So if one of them is true, then the disjunction is going to be true. Does that make sense? Second one, and we're going through and establishing this rule by creating this table. So the first statement is true, the second statement is false, so the disjunction is still going to be true. And likewise, on the third line, the first statement is false, the second statement is true, the disjunction is still true because we only have to accommodate one of those statements. All right? Now, finally, the last one, if the first statement is false and the second statement is false, then both of them will end up being false. The disjunction is also false. Okay? Does that make sense? Okay. As opposed to, turn the page to 171. Now we're going to look at conjunction. Both of them have to apply. So the first and second statement are true, so then the conjunction of them is true. On the next two, because we have to, both of the statements have to apply, if one of them is false and the other one is true, then the conjunction is going to be false. Because we can't meet both of them. If we can't meet both of them, then it's not going to work. Finally, both of them were false, so then your conjunction is false. Does this make sense to everybody? Okay, good. Biggest thing is if you start getting confused with these between conjunction and disjunction, think of a scenario like what I was talking about with the pen and the table. And likewise, and I know I brought this up before, if I have this marker and I'm told put the pen on where it's touching both the board and the wall, well, we can do that. Okay, we can make this work because it's touching the board and the wall. But again, it has to touch the top of the table or the bottom of the table or the floor, top of the table and the floor. Well, we can't make that work, so it's going to be false. That can't happen. So if you start getting confused, think of a scenario to apply to the and the or option, and then figure out if it's going to be true or false, if you can make it happen or you can't. Okay? Cool. Let's look at example number 1. Is this statement true or false? Mars is a planet and the moon is green cheese. Is that a true or false statement? False. Why?
Because they can, and one of the things is false, that makes the conjunction of it false.
Perfect. So what if we said Mars is a planet or the moon is green cheese? Would that be a false or true consideration? True, because with the or, only one of those components has to be true. So Mars is a planet or the moon is green cheese. Well, Mars is a planet, so we got that. We are told or, so that means we can discount that other one. Okay? Easy enough? Cool. All right, then we'll move on to the next section. Now, with conjunctions and disjunctions, I'll turn to page 172 real quick. See that top part up here? That huge, massive chart? Okay, what it is doing is, if it is taking pieces of, if you have 3 statements, and the negation of those, what would take place, and then even the conjunction and negation and disjunction of them, don't let all these symbols confuse you, and don't allow this to be overwhelming. If all you had these 3 statements, P, Q, and R, and you were only told take the conjunction of P and R, you would be able to figure that out, right? Cool, then only do that, and then move to the next one. Now you're looking at the negation of statement R, and that's it. Then draw your chart to only address that. So instead of trying to write out this whole chart and filling in all the gaps to where it's visually overwhelming and you're having to start already consider some of the other options, don't do that. Take it one column at a time and only work with that piece of information. And then you could go through on and on and on and figure this out, and it's really not that difficult. Okay? So that's the important aspect of this, is take it piece by piece. Any questions about that? Yes, no, maybe so? Cool. All right, so let's, we'll move on. 5.4, we have three more sections to go. So we'll cut through these. 5.4 is a conditional statements. Okay, so if you look on page 176, the definition of a conditional statement is a statement of the form if P then Q. Okay, where P and Q are statements, And then the notation for this is going to be this. So if P, then Q. So if this happens, then this is what the result will be. And it's important that you read it in that order. It is not if Q, then P. It is actually the other way. If you have this first statement, then the second statement. And that is a conditional statement, and that kind of just makes sense. It's a condition. If you pay at the counter, then you will get your hamburger. Well, that just makes sense. Unless you end up robbing the place, but even then, if you rob the place, you will go to jail for a really long time. So it's still a conditional statement. And so here we look at example number 1. There are no clouds in the sky, so it is not raining. So what it's asking us to do is rewrite this as a conditional statement, to where you have if. And so if then, yes.
Oh, that wasn't.
Okay. So if any of you have ever done, well, some computer programming or messing with computers, there's the if-then statements that also exist. So you create parameters of how your computer will work or run, or applications, even gaming's is done. It's done with this. If this person pushes B, then this result will happen up on the screen. And so it's just a whole bunch of if-then statements. So here we have, there are no clouds in the sky, so it is not raining. We need to change that to an if-then statement, or a conditional statement. If there are no clouds in the sky, then it is not raining. School will be canceled if a blizzard hits. If a blizzard hits, then school will be canceled. So it's being renamed as a conditional statement. Okay? So let's, and this is going to be kind of a confusing component, so I want to walk through this. Okay, page 177. Okay, how do you determine the truth of a conditional statement? And so we're going to look at a truth table for a conditional statement. So we have statements P and Q. It doesn't matter what they are, and then P is a condition, or Q is a condition of P. If P, then Q. Well, if we have, and I'm not going to write up the whole table, but P, Q, and then if P, then Q. So if P is true and Q is true, well then this is going to end up being true. Okay? If this statement is true, results in a false, okay, where the second statement is false, then what would be the truth in this? So let's look at this way. The example they have is Roo is a kangaroo. That's true. We can verify that it's a kangaroo. Then Roo has wings, which is a false statement, right? So then that's actually going to be a false statement overall, okay? Because he's not going to have wings because he's not, that's just doesn't happen. It'd be kind of cool to see, really. I'd love to see a kangaroo with wings and it just like takes off. And especially if it has like one really huge wing and one tiny little chicken wing. So then whenever it flies, it can only fly around in circles. It doesn't really quite get anywhere. Well, that'd be kind of interesting. So, now the last two, okay, if we have, and let's scoot down here, if the first statement is false and the second statement is false, because if one is false, then the other is false, they will end up creating truth, okay? Because both of them are false, that creates truth. Does that make sense? All right, this is false, yes, we agree. Both of these result in a true false, if that makes sense. But the second one would be kind of confusing. So we have a false statement. This results in truth, okay? And let's read the example that it gives here. Suppose you said, if it rains, then the creek will flood. You did not lie, even if it doesn't rain, because you said if. Okay? If the creek rains, or I'm sorry, if it rains, then the creek will flood. Well, there are other options that on the if side of things doesn't make it definitive. It doesn't say always, it doesn't say every time, okay? It says if. So if it turns out that it doesn't actually rain, the creek really still can flood from other measures, so it can still be a true statement. Does that make sense? This part is not definitive. This one is going to be definitive. The second statement will be more definitive. That's why in this first one, it was true, but it resulted in something false, so then it is a false statement. Okay? Cool. Does all that kind of make sense? Kind of confusing at first, but the more you stop and reason through it, then you'll actually get really fast at these. Just like with the logic problems. I used to do those. I kind of got into them for a while, and the first ones I started doing, then I started timing myself. And then I really started flying through these things because I began to know what to look for. Excuse me, it's just all by habit and usage and so on. Kind of like, we love soccer ball. You have a kid that just starts kicking a soccer ball. Well, it's going to be kind of goofy looking. They miss it or they kind of hit it weird. But then years of working at it, you're juggling bicycle kicks, headers, all sorts of stuff, and you're going crazy with it. Basketball, karate, whatever. It's going to be kind of interesting to do a roundhouse, and now you can knock somebody clean out because of your technique. Now, let's move over. There are two more areas that we're going to look at in this chapter that are actually, now that we understand that, are going to be easy. Page 178, there is biconditional statements. Biconditional. Okay, so this is where we're going to see, if we're looking at P and Q, we have statements P and Q, and it's going to be symbolized with the arrow going both directions in between both of them. Okay, so this is P, the P statement, if and only if Q. Okay, so the first statement exists only if, or is true, only if and only if Q is established. Okay, and from there you can kind of look at your truth table. We'll just go through it real quick. So if the first statement is true, second statement is true, then they're both true. If either one of them are false, then they will be false. If they're both false, then it comes out to a truth. This is false, yes, that's true. They are both false. Okay? So biconditional. Now finally, we have three more to look at, and I want y'all to write these down as far as definitions. Because and we're going to go over an example of it. This is actually really easy, and this makes sense once you look at it. The only issue is you're going to want to refer back to which statement means which. Okay, which one was converse, which one was inverse, and which one was contrapositive. So make sure you write each of these down. So converse is a conditional statement, and it's obtained by switching the hypothesis and the conclusion. Okay, so the converse of if, whenever you have statement if then, you have a conditional statement. Well, the converse of that would mean that you take the second statement and it would be a conditional for the if Q then P. So you actually swap the statements on a condition. The inverse, and let converse. The inverse is going to be when you have your first statement, or your two conditional statements. Well, then the inverse is going to be the negation of both of those still in the same order. It'll be the negation of both of those still in the same order. And then contrapositive you will start off with your conditional statements, but now they will be the negation and the converse of that statement. So it'll be the negation of Q and the negation of P is it's still as a conditional statement. So if you just memorize this, which really, again, the first one, all you're doing is switching the statements. The second one, you're keeping them in order, but you're negating both of them. Then the third one, which is kind of really the only other option, really, is you're negating both of them and then swapping the statements on either side of the conditional arrow. And that's it. So let's take a look at this. We're going to write the converse, inverse, and contrapositive of the implication below, which we're an example for page 179. So if we have a blizzard, then the school will be canceled. The converse would be, if the school is canceled, then we had a blizzard. Okay, so notice how we switched those statements. Still an if-then statement because it's conditional. The inverse is, if we do not have a blizzard, then school will not be canceled. So we took the negation of the same statements in the same order that they were in originally, just the negation of both of them. Then the contrapositive is, if a school is not canceled, then we did not have a blizzard. So we took the negation of those two statements as they were rearranged. That's really easy. And you'll have to do that in your homework, and it's actually really easy. I believe in all of you. Y'all can absolutely do this and be effective. Good job. I'm already proud of you. All right, any questions about that section? Alrighty. Somebody turn to page 5.5 and tell me what the title of that is.
Proofs.
What? I didn't hear you.
Proofs.
What? You sound so depressed. Proofs. Okay, so we're going to be looking at proofs. 5.5, we're looking at proofs. Here we have to establish a few things, okay? And it's really not as difficult, and every time people hear proofs, you're like, oh man, and your brain immediately goes somewhere else. This really isn't that hard, and we're not going to be doing a whole line of proofs, okay? It is important, though, that we understand what is actually taking place whenever we are proving something, okay? But we have to understand what's taking place. So a few more definitions that y'all will want to write down. One, a proof is a system of reasoning or argument to convince a person of the truth or statement. So this is really easy, okay? I am proving to you that this carpet is not made of leather. And so I begin to explain different, or create or make statements that prove to you, or that show that there is no leather in this carpet. And we can talk about the texture, the fiber, the color, receipts. I mean, we can go all sorts of places, where it came from, and the person that testifies, yes, I made this, and I did not use any leather products to make this carpet. I mean, you can go on and on and on. You can make these proofs as long or as short as you need to. Okay, but it's just a statement or an argument to convince somebody of a truth. So then, with that, we have inductive and deductive reasoning. And this is important to understand the difference between these two. Inductive and deductive. So, inductive means that, again, these are arguments, that something is probably true. Probably true. Most likely, seems like it is, but it's not quite definitive. It is probably true. Deductive is an argument that states with absolute certainty that this is true. This is absolutely true. Okay, so police officers, okay, they have this ability to investigate crime or circumstances. So that is called reasonable suspicion. Okay, I have reasonable suspicion that something is going on, some sort of crime, based on what somebody reported or factors that are taking place. So I have the right to go and contact this person as a police officer and investigate the crime. That is inductive, because it's probably true, but it might not be true. Okay, I think that this person was breaking into this car because it's late at night. He's walking around the car and shining a flashlight in it. I can go talk to him. It looks like he's breaking into a car. Okay, now I contact him and I start investigating, and I see he's wearing gloves. He has a purse around his shoulder. I contact the owner of the car, and they're like, that's my purse, it was inside my car. There's a broken window, and he left his footprint, because he took his boot off and whatever and decided to leave some evidence, so he put his footprint on the car. Okay, absolutely true that he broke into this car and committed burglary of a vehicle. Okay, so you kind of see the difference between the two. And that's what inductive and deductive reasoning is. All right, now in doing so, we have an argument that is valid or an argument that is sound, and we're now looking at the definitions on 183. An argument is valid if the reasoning proceeds logically from the premises to the conclusion. Okay, now a premise or the premises is the supporting statements that give credence to what you're trying to get to your final result. Okay, so it's all those statements that I just explained of how we know that this guy actually broke into the vehicle. All right, and then the conclusion would be this guy committed burglary of a vehicle. Make sense? Okay, so an argument is valid if the reasoning proceeds logically from those statements all the way to the conclusion. An argument is sound if it is valid and then you find out that the premises are true. Okay? So not only do we have the ability to kind of reason our way through, but then we found that each one of those statements were absolutely true, so then our argument is considered sound. You understand the difference between the two? Anybody nod? Is it still kind of confusing? No? Okay, cool. So let's look at, look at example number 3. Analyze this argument. Is it deductive or inductive? And then identify the premises and the conclusion, and is the conclusion valid and is it sound? Okay, if a man is saved, then he is a Christian. If a man is a Christian, then he should display the fruits of the Spirit. Therefore, if a man is saved, then he should display the fruits of the Spirit. And this is coming from Galatians in the Bible. Okay? So first of all, is this deductive or inductive reasoning? Y'all tell me. Without looking at your book or anything below that, don't look at the answer. But is this inductive or deductive reasoning? Because what's the difference? We have probably true or absolutely true. Deductive, yes. Especially if you are a Christian and believe in the Bible, then that is absolutely true. If a person is saved, they should display the fruits of the Spirit. Okay? Now, The first two statements made there, those are the premises. Okay, those statements made are the premises, and then we have therefore, and our final statement, that is what? What is that called? We have the premises, and then what?
Conclusion.
Conclusion, yes, very good. So our first statement's our premises, then we have our conclusion. Finally, is it valid? Is what is being stated valid? The reasoning proceeds logically from the premises to the conclusion. Is it logical what it's saying? What do y'all think? Raise your hands if you agree or if you agree. Okay, awesome. So is it sound now? Are all the premises, the statements leading to the conclusion true? Yes, they are, so this is also a sound argument. Okay? It's pretty easy, right? Awesome. That is that. Finally, we go to 5.6. Now, we are going to learn some weird words in this section, and then we are done. What I will say is 5.7, we're not going over 5.7. Your homework tells you to do a few things. There are exercises to perform constructions, but all you need to do is follow the exercises in that section, okay? It'll tell you what constructions to do on there. There's 3 of them. And basically all you have to do is follow the instructions on how to create those constructions, okay? Any questions about that? It'll be easy. It's not homework that you don't know. All you're doing is following what it tells you to do. All right, 5.6, we have deductive proof, and we're going to look at, if you see those first 4 terms at the top of page 189, we're going to need to know all 4 of those. Law of deduction, modus ponens, modus tollens, and transitivity. Okay, you're like, what? What? Yes, there are odd words, okay? But, again, once you write them down and you refer to them, you'll know which one to use. All right? We are going to study 4 types, and these are all deductive arguments, okay? There are others that exist, but we're only going to be focusing on these 4. And the law of deduction is probably the most important, honestly, of all of them. It's what we end up using on a day-to-day basis more often than anything else. Okay? So, let's turn to page 190. The law of deduction is a method of deductive proof, and then it shows the following symbols, okay? Where the first statement is assumed, and then you have other statements that are known to be true. R is going to be deduced from other statements, and then we have our conclusions. Okay? So, we're going to look at a proof, example number 1, to try to understand this. We're going to have to prove that if T is the midpoint, point T is the midpoint, and you can see right here there's a segment, a line segment, and you have points S, T, and V. If T is the midpoint of segment SV, then ST is 1/2 of SV. Okay, segment SV. Alright, so we start off with what our assumption is. Okay, T is the midpoint of segment SV. Okay, well our first statement is ST equals TV, and STV is your segment with T being that midpoint. Well, then that's the definition of a midpoint. If we add both of those, the 2 half segments, to equal the whole segment, well, that's the definition of between. No. No. It's just between. No. The other word is not a real word, and it drives me nuts. It's like running electricity through my body, so we will not repeat the word. It is simply between, with no other continuing sounds or syllables to know to address to that.
So you
And we
don't
will now
listen.
know, and now we will move on. We will move on. So the next statement is whenever we do the first half, so if we have the first half segment and the second half segment, that equals the whole segment. Another way to prove this is if we take the first half segment and add it to itself, well then that still gives us the whole segment. What this is saying is we have STV. Well, if ST plus TV equals SV, well then what we can say is these two are equal half segments, or segments half of the whole. So then ST plus ST should still equal SV. So looking at this, what do you think we can conclude? If we add this plus this, and it equals the whole thing, this plus itself equals the whole thing, then what else can we?
T is the midpoint.
We're getting there, yes, but right before that, what about in relation to S, T, and TV? What about them?
That they're equal.
Yes, absolutely, that they would end up being equal, right? And also, if we have, since we add these together, we could also say that 2 times ST would equal the entire thing. And then, so then by saying, I'm going to move this actually over here. So 2 times ST equals SV. What we can do is get ST by itself. So we divide by 2, and whatever you do to one side, you do to the other. So ST equals 1/2 of SV. Does that make sense? And that was getting to our original statement. So if T is the midpoint of SV, then ST equals 1/2 of SV. So we're starting off with our original statement that T is the midpoint of segment SV. How do we get to this point right here? That's what a proof is, okay? What information, definitions, and so on have we been given and established to go step by step to get to here, okay? Geometry typically has a lot of these. We will not have a lot of these because it's more along the lines of understanding the process than it is doing a bunch of them, because there are other things that we could be learning that we're actually going to hold on to for a longer period of time. Okay? Now, real quickly, because we have about 6 minutes, modus ponens. So any questions about how we started from one and worked our way through? Okay. Modus ponens is a method of deductive proof with the following symbolic form. If we have premise 1, okay, statement P and Q are conditional statements. If P, then Q. The second premise is we have P. Well, then our conclusion is we will have Q. Does that make sense? If we are told that these two statements are conditional, if this, then this, okay, well, we have this, well, then our conclusion is, well, then we will have the second statement too. If we have the first statement, then we will have to have the second statement, because we've already established that if one exists, then the other one does. Okay, pretty easy, right? That is modus ponens. Okay, it is the method of deductive proof that shows that if you have a conditional statement and then you have one of the statements, you will have the other. Modus tollens, then, if we look down on page 191, it's a method of deductive proof where if you have your conditional statement, if statement P, then statement Q, well then you are told that you have the negation of Q, well then you will have the negation of P. So let's look at this. Okay, actually we'll do this. Let's say red and black are opposite of each other, okay? Now, for your modus ponens, we have, if I draw a black dash, then I will draw another black dash. Okay? Well, or actually I'll draw a black A. Okay? Well, according to our definition here at modus ponens, if I have now drawn a black dash, so what must happen?
You must draw a black A.
I can't help myself, I have to draw a black A, even if I'm trying not to, because of this conditional statement up here. If I do this, then that's going to happen. I don't know, let's try it again. Let's see what happens. Alright, I drew it there. Alright, yeah, I had to draw another one. So see how that works? It's that simple, right? Cool. Now again, we have black and red, they're negations. If we have, I'm going to do a different example. We're going to do a black dash and a red dash. Alright, so if I draw a black dash, then I will draw a red dash. So modus tollens is going to tell us that if the opposite, okay, this is Q, the opposite, let's see, if I end up doing the opposite of this, then the opposite of this will exist. Does that make sense? Maybe I should have drawn an A again. So I do a red A. Well, since I have now done the negation of that, a black A, then the negation of the first statement is going to occur. Does that make sense?
Yeah.
Okay, now again, it's going to be kind of confusing, just in the sense, okay, which one was which, because it makes sense to everybody, but so make sure that you write it down, make sure that you refer to those, especially instead of guessing at these, or like, okay, I think I remember what it is, let me go confirm what I know, and then write actual correct answers on your homework assignment, okay? Don't guess. Don't assume anything. You have way too many resources right here in front of you, and we've covered a lot of information today for you to remember everything. Okay? Any questions about that? Finally, transitivity. If I have transitivity involves three statements. If I have this, then I have this. Well, then what?
Well, if you have the dash, then you have the.
That's right. Then I have this. Easy enough, right? Awesome. That is everything. Again, on 5.7, you're going to reconstruct, follow the examples given in the front part of your assignment. You won't actually have to do any of the actual homework part of it, okay? It's just the examples given. And good day today.